Hello students, till now we have been dealing with the topic of electrode potentials, standard electrode potentials in this electrochemistry, and today we will be talking about the Nernst equation. Okay, so what is that Nernst equation? So Nernst equation. Okay, see, before coming to the Nernst equation, what we will do is that we will just little bit will touch the initial past, what we have talked about. So for example, we talked about, so I'll write here till now so that you get it that what we have done. We have talked about the standard redox potentials or standard electrode potentials, isn't it? We have talked about these standard electrode potentials or the EMFs, okay? Standard electromotive forces of the cells. Now, in this case, the word standard here refers to what? What do you mean by this? This refers to the standard conditions of temperature and pressure. That is here, temperature is 298 Kelvin, okay? And pressure is already 1 atmosphere. That's what we take, or 1 bar. Normally, standard conditions, it's 1 bar or 1 atmosphere, even you can take. And what you take is that you also consider the concentration of the electrolyte, that is 1 molar. Okay. So when you have this kind of a condition, the electrode potential at that time is the standard electrode potential. For example, you have the standard electrode potential and you denote it by E naught. Okay. So standard potential of an electrode is denoted by this, like for a metal in its oxidized state to a metal in its reduced state, that will be some value. Okay. So for example, you have copper 2 positive to copper, and you know this value is 0.34. That's from the values. You remember everything with this with the time. And similarly, you know that the standard electrode potential of zinc 2 positive to zinc, that is minus 0.76 volt. Okay, isn't this? So, but these are the standard values. No? The temperature is 298 Kelvin. The concentration of this zinc and copper is 1 mole. Now, what I am asking is that, what if we have a non-standard condition? Okay, we'll use the non-standard condition. What if the conditions are non-standard? That is, what are non-standard conditions? Non-standard conditions means that temperature is not equal to 298 Kelvin, and especially the concentration is not equal to 1 mole. Okay. So either you can change one of the two factors, either temperature you will change or the concentration you can change, or you can change both. Both of them are non-standard condition. So for now, what we will be dealing with is that we will be keeping the temperature is equal to this 298 Kelvin. We will keep it 298 Kelvin, but this we will change. Okay, this we will vary. So therefore, there is a question. Okay, this is the electrode potential under the standard condition. That is, the concentration of the electrolyte is 1 molar. But when the concentration is not 1 molar, what will happen to this electrode potential? Will it be same? No. Then there will be some change. So in order to obtain the electrode potential of this half cell, or even the EMF of a cell, under the conditions where the concentration is not standard or even the temperature is not standard, we have the Nernst equation. Okay, there is the, so therefore what the Nernst equation gives you? Nernst equation actually gives you the EMF of a cell under any condition. Even if you use the standard conditions there, you will get the standard electrode potential as well. So under any kind of so what does the Nernst equation say? It says that for any reaction, okay, like such as, if we take, we have M in oxidized state and it is actually getting reduced to form metal in its solid state. So for any reaction like this at any concentration and temperature, electrode potential, electrode potential is given by, okay, or what we should write is that in front of electrode potential we should write here E. Electrode potential EM and to M solid is given by given by what? E M N to M solid, or even in its reduced state. I may not write here solid always. Even we can do one thing. We can simply write here M. Okay. It will be given by. So that will be given by the standard electrode potential of this redox couple, that is this, minus RT, what is R? I'll tell you, by NF natural log of the product side, this, the concentration side of this, divided by Mn positive. In aqueous, it can be in aqueous state as well. And one more thing is there, I'll tell you here, if there is some stoichiometric coefficient here x, okay, then you need to actually give this stoichiometric coefficient here, okay. That is the complete redox, that's the Nernst equation. So what does this Nernst equation say? The electrode potential in any condition of temperature and concentration, okay, is given by the standard electrode potential, what we have talked earlier about, minus RT by NF. What is R? R is the universal gas constant. Okay, so I will write it on this side. Oh, we'll write it with the black only, or yeah, black. This black will be better. So what is R? It is a universal gas constant, and its value is 8.314 joule per mole per Kelvin. Okay, and temperature. T is, you know, temperature in Kelvin. You always need in Kelvin. Okay, you need always, whenever, if you are given the temperature in degrees Celsius, always convert it to the Kelvin. And then we have this F here. What is this F? F is Faraday's constant. Okay, it is Faraday's constant. And what is that Faraday's constant? It is nothing but the product of the Avogadro number, that is this, multiplied by charge on each electron. Okay. So it is actually the charge on 1 mole of the electrons. So therefore it is, you know, it is 6.023 into 10 power 23 multiplied by 1.602 into 10 power minus 19 coulomb. And then you get the value, it's nearly equal to 96500 coulomb. Okay. And actually it is a little bit less than that, but the difference is not that much. So we keep it like that. Okay. So that is the Faraday's constant. Now we have this, isn't it? Now can we write this equation? E is equal to like this, E naught minus 2.303 RT NF log of this. See, this is the molar concentration of pure solid, and you take it unity. Okay, so we can keep it 1 by Mn aqueous. Okay, and it's powered by x as well, because if there is some coefficient here. So why we have written it there? Because when you convert the natural log into the log, then you have this conversion. Remember, ln of x is equal to 2.303 log of x. Okay, that is the thing we have used here. Now see, if I told you that we will change the concentration only, if we keep the temperature at 298 Kelvin, we know R is 8.314, F is constant, everything is constant other than this N. Okay, what is this N? Okay, N is the number of moles of electrons or number of electrons involved in a reaction. Okay, number of electrons involved in reaction, that's the how many number of electrons or the number of moles of electrons are involved in a particular reaction. Now since this can change, okay, but all of this part is constant. You see that if we take temperature, this part, if we take temperature 298 Kelvin, this part comes out to be equal to, so we will get this kind of a thing. We can write E is equal to E naught minus 0.0591 divided by F. When this is only possible when you take temperature. So maybe I can just erase it so that it becomes a bit clearer to you. I'll just erase all of this and I can just do one thing. If T is equal to 298 Kelvin, okay, then what will happen? E will be equal to E naught minus 0.0591 divided by N log of 1 by Mn positive power x. Okay, that is the redox reaction. Sorry, Nernst equation what we use. Okay, this is the most used form of Nernst equation. Okay. Some people call it a Nernst equation and some say Nernst equation. So it doesn't matter too much. So you should know the concept as well. Okay. So just we should at least before completing anything, we must do one thing. We must always go for a numerical, isn't it? So we are here asked that we need to calculate the reduction potential of a cell at 298 Kelvin. The reaction is this. See, if you are given the reaction, you are given Ag positive in aqueous state plus 1 electron. It changes to Ag positive. Sorry, it will not change Ag positive. It will change to the Ag in solid state. And what you are given is that the concentration of Ag is, you are given that Ag positive is 0.1 molar. See, it is not the standard concentration, it is the non-standard, it is 0.1 molar. Okay, and the temperature is 298 Kelvin. Okay, now you know that the Nernst equation at 298 Kelvin, what will it be equal to? And one more thing we need is that the standard reduction potential of Ag positive to Ag, it is given by 0.80 volt. Okay, now what you need to find out? You need to find out E, okay, at this concentration. So what will be E equal to? Ag positive to Ag, obviously it will be what? E naught Ag positive to Ag minus 0.0591 divided by N log of 1 by concentration of Ag positive, okay, in aqueous state. And there is the stoichiometric coefficient is 1, so there is no need to write. Now you can use these values. Here it is 0.80 volt minus 0.0591. Now how many number of electrons are being transferred? 1 electron. So it is divided by 1 log of 1 by 0.1. Now let us solve this log of 0. This log of 1 by 0.1 means 10 power minus 1. Okay, and therefore it will give you minus 1 into log 10, which will be equal to minus 1. Okay, so this you should know that it is m power n, log of m power n is m log m, and then log 10 is 1, so it is 1 into minus 1. I'll write it like this. So this will be minus 1. So therefore this, the value of this is minus 1. So when minus 1 is multiplied with this, it will become plus 1. So it will be 0.80 volt plus 0.0591, isn't it? No, a little bit of mistake is there. Yeah, it is actually the log of, let's clear this first. I'll erase this first. So yeah, what is this? It is log of 1 by 10 power minus 1. Okay. Now when it goes up, it will become log 10 power 1. So it is log 10, which is equal to 1, not minus 1. Okay. So therefore here it will be plus 1 into the minus. So therefore here it will not be what? It should be here minus, because this comes out to be plus. Okay. So what will be the value now? When you minus this, so the exact value will come out to be, if you just get the difference, 10 minus 9 will be 1, 9 minus 5 will be 4, and 7 minus 0. So it will be 0.71741 volt. Okay. So this is the standard, this is the electrode potential of silver electrode in you can say when the concentration is different. Okay, just one more thing is that you know already that okay, this is the electrode potential. How do we now get the EMF of a cell? Okay, so what do we do that for the EMF of cell? EMF of cell from Nernst equation. Okay, from Nernst equation. So what we will do is that you know what is EMF of cell? E cell किसके बराबर होता है? It is equal to E cathode minus E anode. Okay. So till now we have only talked about the standard electrode, standard EMF of the cell. Now when you don't have the standards, you can write it without standards. Okay, like this. So for example, you have any cell in which I'll take the example of Daniel cell. What is Daniel cell? What is Daniel cell? The cell is this, in which zinc is converted to zinc 2 positive, okay, in aqueous form. This is the double, or you can say the salt bridge what we show, and then copper 2 positive is reduced to copper solid. Okay, this is the cell. So you must know that while representing the cells, this part is anode, okay, and this part is cathode. Cathode is that part where the reduction takes place, which means that where the cations will go, and anode is that part where the oxidation will take place. Okay, so what will be the E cell in this case? What will be E cell in this case? It will be what? E cathode, you know that it will be E zinc 2 positive to zinc minus E copper 2 positive to copper. Okay, now using the Nernst equation, you can do these two separately. Okay, you can do these two separately. So, oh yeah, there is one mistake. It should be E cathode minus E anode. Yeah. So what we should do is that it is E cathode minus E anode. Okay. So what is cathode? It should be E copper 2 positive to copper minus E zinc 2 positive to zinc. Okay, that is E cathode minus E anode. Now using the Nernst equation, what we have talked about already, you can just write the values, isn't it? What you can write, you will write here E naught copper 2 positive to copper minus 0.0591, taking the temperature to 98 Kelvin, isn't it? That is the divided by n log of what? 1 by copper 2 positive minus, now we'll keep these two in brackets, E naught zinc 2 positive to zinc 0.0591 divided by n log of 1 by zinc 2 positive, just like what we did last time. Okay, अच्छा, see अब हमें क्या करना चाहिए यहाँ पे? Okay, I need to erase this because I don't have too much space here. So okay, what will be the E cell in this case? If you see that this and this can be taken separately, it will be E copper 2 positive to copper minus E naught zinc 2 positive to zinc. Okay, now this minus will be positive and this will remain negative, isn't it? This will become positive and this will remain negative. So therefore what should we do? We will do that, we will write this first minus this. So it will be minus or I'll write plus 0.0591 divided by n, that is this minus plus log of 1 by zinc. I take this common, isn't it? This 0.0591 because n is same 2 on in the reaction. So I'll write minus log of 1 by copper 2 positive. Okay. When you do this, this will be equal to E naught cell. Okay, this will be E naught cell plus 0.0591, 0.0591 divided by n log of, now see what will happen. This is minus, but this is in the denominator. So this will become positive if I take it up, and this will become negative if I take it up. So therefore this will be log of copper 2 positive minus log of zinc 2 positive. Okay. So therefore we will get log of copper 2 positive by zinc 2 positive. Okay. But this is the case when we keep plus there. Okay. When we keep plus, if we keep minus here, so what will happen here? Or you can write here, it is P naught cell minus 0.0591 divided by n log of zinc 2 positive by, you need to write it properly, otherwise it always keeps a mess. Zinc 2 positive divided by copper 2 positive. Okay. And what is zinc 2 positive? It is anode and this is cathode. So what will be the general reaction? In general it will be E cell minus 0.0591 divided by n log of concentration of anode divided by concentration of cathode. Okay. That is how you get the EMF of the cell. Now, if you are given the concentrations of the two, you can easily calculate the EMF of the cell, provided you are given this value. Okay, you need this value as well. This should be given and the concentration should be given. Not only that, what you can be asked, you can be given this and these, you can be asked how many number of electrons have been transferred. There are so many questions which will be asked. And remember, this is one of the most important topics for the 12th board as well as NEET and JEE as well. Okay. Rest there were some numericals, but maybe it will take more time. So thank you very much for this. We're done. Okay. So I think you have heard everything and you understood the things. Rest whatever is left, we can do it in the next lecture. Bye.